All right, so I wanted to, I guess, make this video about a method in numerical analysis that I'm fairly interested in. And I told myself that I probably wouldn't make any videos on things that I'm currently learning, or at least things that I've learned, but I'm still taking the course for. But I feel I have a good enough understanding on this, and I don't think it would hurt anyone really. And I try to be as concise as possible as far as my definitions and proofs go. But that being said, I wanted to treat it more as an overview anyway. I'm not really going through any computation because that would take way too long and would mainly involve code, like MATLAB or something. But basically what I'm talking about is something called interpolation, specifically polynomial interpolation, as well as I'll briefly cover what splines are. And then I wanted to finish off with something called Runge's phenomenon. Runge, I forget how to pronounce it. It's German, but I usually just call it Runge. So anyway, polynomial interpolation, I guess, is what we'll start with. And then we'll go to all the other stuff. So I think I'll probably include the LaTeX that I use to make this under the video, I guess, if anybody wants to use it for school or whatever it may be. If anybody sees it, I don't even know. But I like it. I made it. I'll sort of keep it as a note for myself. I like the topic, and I think I want to research this more if I go to grad school. So I kind of like that I'm preparing on it. But anyway, so the first topic of this, which gets us into everything else, is something called interpolation. So what is interpolation? Well, let's imagine that you have some complex function, such as a crazy parametric equation that describes some fancy curve, such as maybe this rubber ducky that I included below. But there's no such thing as the rubber ducky equation. You can't just go and derive an equation that perfectly creates this 3D rubber ducky as one equation. I know that you could probably go in Desmos and do a bunch of equations, which is essentially what we're talking about today. So how and why would you want to approximate this complex function? Well, as I was just mentioning, let's imagine you have this rubber ducky. Imagine this is some graphic in an animated movie or video game. If you were a graphic designer or a visual effects artist, how would you actually design this on the computer? I don't think it would be possible necessarily. At least, also, let's assume we're in the year 1997, just for the sake of this. I don't think you could just draw perfectly around and create all the depth of this and then yield this rubber ducky. So instead, you would get a bunch of smaller, simpler functions and add them together in certain spots to essentially create the form of this rubber ducky. So it's not exactly the rubber ducky, but at certain spots it looks exactly like the rubber ducky. And this is probably why on video games, even today, but especially way back in the day when they were doing things like scanline, if you zoom in, you could see the polygons that make up the character. And they still, to my understanding, still use polygons because they're really simple shapes. So as far as the code, it's really easy to calculate the area and stuff of them. But imagine a game like Tomb Raider and the Lara Croft character, you can very easily see just how jagged her elbow is. And that's because that's just a consequence of the time. But they are using things like splines, which we'll talk about later, which is just a way essentially to take a complex shape or image or function and break it down into simpler functions. And in the case of interpolation, this is exactly what it is. Now, it is important to mention that interpolation was not initially just discovered for graphics. I mention graphics because I think at least it's a very intuitive way to think about it, sort of like composite images. But as we'll find out with Runge, the mathematician, he was doing things with interpolation way before computer-generated imagery or movies in general, I think. So it was initially designed to help mathematicians work with these massively complex functions, such as finding out values for logarithms back before they couldn't just go to Symbolab or use their graphing calculator. So there was actually like books of logarithms and trig identities that existed, which sounds like hell. I can't imagine doing that in school. So if you wanted to know the value of a certain logarithm, you would have to literally go in like a logarithm book into a chart and find that value. And the way that they got those values sometimes was by using interpolation to basically break down a big logarithm function into simpler polynomials, which we'll see now, and find approximate values. So yeah, and specifically this image that I reference is free-form vector graphics with controlled thin plate splines. We won't talk about thin plate splines. That's just a type of spline, but we'll talk about splines. So as I was mentioning, think about the simpler functions that could make a more complex function. This is the basic thought process behind interpolation. So now we'll get into the definition stuff. I want to mention that this will involve a lot of math, but it's meant to be an overview. So we'll just involve like general proofs and definitions, but I wanted to try to stay as general and rigorous as possible when it comes to the math. So don't expect there to be like full proofs on like how to derive like the Lagrange basis functions or something like that, but I will cover them and sort of like maybe you could say like the algorithm, the pseudocode for actually finding these interpolating polynomials. So given a set of n+1 data points, x naught, y naught, and we're just going up to xn, yn, with now two x sub j the same, a polynomial function p of x, which is the term a naught up to a sub n x sub n, so this is just a general form of the polynomial, is said to interpolate the data if we can find some polynomial of x sub j that's equal to y sub j for all j in the set 0 to n. So what does this mean? Well, given some data for a more complex function, we just want to find a polynomial that's equal to that data for every point on the interval or the set that we're looking at. And this is what we call interpolate or interpolation. So this is the general idea behind polynomial interpolation, but when it comes to actually finding this polynomial, p of x sub j, there are a lot of techniques. I will discuss 4 in this video, I guess, but there are, I would guess that there's probably hundreds. I think it's just one of those things that mathematicians look at like the old techniques and then they build on them over and over and over. But the ones I'm going to discuss today are very basic and only require like knowledge of some linear algebra and calculus. So, before I actually cover the ways to do it, I will mention the interpolation theorem, which is, this is the big theorem that sort of is the basis for how we treat interpolation. And so, as previously mentioned, for any n+1 bivariate data points, so x naught, y naught up to x and y, and we want those to be in the vector space R2, which is fine. It doesn't matter. Yeah, you can consider the 3D case, but we're just thinking of either single variable functions or multivariable functions in 2 variables. So we're no 2 xj are the same. Then we say that there exists a polynomial p of x of degree at most n. That's very important. We say degree at most n. That interpolates these points. So i.e. p of x naught equals y naught all the way up to p of xn equals yn. So we would say that p of x sub 1 equals y sub 1, p of x sub 2 equals y sub 2. So as previously mentioned, we want some polynomial to equal our data point for every value of I on the interval. Equivalently, for fixed choice of interpolation nodes x sub j, polynomial interpolation defines a linear bijection, L sub n, between the n+1 tuples of real numbered values, which belong in the vector space R n+1, as well as a vector space P sub n, which defines the space of all real polynomials of degree, again, at most n. So that is to say, and I just wrote the shorthand for this, we're looking for a linear transformation L sub n, which just takes us from the vector space R n plus 1 to the polynomial space. So this isn't real important. This is more like, I just sort of included this to stay as general as possible, but this is not something you're using. This is just the theorem behind it. So now let's actually get into some of the methods to do this. So first is, at least what I learned first, is the monomial basis. So I'd say that this is probably the easiest way to find an interpolating polynomial. But as we'll find out, it is not remotely close to being the best way. So we call this a monomial basis, and we want to let our polynomial have the general form a naught up to a n xn. So again, that's just the general form of the polynomial. And of course, we said at most n, so we want to apply n plus 1 conditions to the polynomial. And all this does is create indices for us. So we could just rewrite it as p of x sub I equals a naught. So then we have our first a coefficient, a1 xi, all the way up to an x sub I to the n. And again, that's for I in the set 0 to n. So we're not really doing much. We're just adding some subscripts to indicate, I guess, that we're working in the discrete case. Or more conveniently, and how we generally see it, is we use the following linear system defined by the Vandermonde matrix, which is given by the matrix on the far left. Yeah, if you've never, I guess, seen linear algebra, this seems complicated, but it really is just a group of linear equations. So the easiest type of equations to solve. And all we're doing is using matrix notation, and the things a naught through an and y naught through yn are just column vectors, which just represent the coefficients. And then I mentioned that is to say that we can solve for the coefficients a is equal to v inverse y. So generally you would set the system up as va equals y, but you can rewrite it as a equals v inverse y, which is just a consequence of the system itself. So what you'll find out is that generally we're concerned with the coefficients in the actual process of finding this polynomial, because we know what the general form of the polynomial is going to be. So if we're working with a second order, we know that our greatest value is going to be like x squared, but the only thing missing from that really is the coefficients generally. So that's what we're solving for. So that's why I specifically isolate a here. And so they are bolded, so a is a vector and y is a vector, and then v inverse is the inverse of the Vandermonde matrix, which is this on the far left. And we usually denote this as capital V. And so again, though this seems very simple to set up and solve, this system itself is terribly ill-conditioned and is going to be favored for these other techniques. But ill-conditioned in the numerical sense means that it's not going to be good for time complexity when we're actually computing on the computer. There's going to be too many operations, and you're going to run into a lot of errors when you're actually, it's not going to run on a good thing like O of n squared or something. So I don't know if I want to talk about Newton polynomials first or this first. I guess I put this first, so we'll talk about this first. So another method to find this polynomial is Lagrange interpolation. And rather than setting up some system like this, the whole idea behind this method is to use what's called the Lagrange basis functions, which are these functions that the mathematician Lagrange made, and we can use them as what I refer to as on and off switches. But doing this, we can then find an interpolating polynomial, again given n plus 1 data points. And so I have that over here. So this is the general Lagrange form, so usually denoted as lowercase l. And all it is, it's the sum of the products of the differences, generally, you can think of. So x minus x sub m, x sub j minus x sub n. And the conditions are very important. M cannot be equal to J, which I think you can see why that would make sense, because we don't want 0 minus 0. We don't want to run into an indeterminate form. As far as programming, that would be very bad, but also just pure math in general. And then we're on the interval 0 to n, where m is between 0 and n. And so after we take the sum of products, denoted by capital Pi, we then find that the resulting polynomial p of x is simply just the sum of whatever we found from the general Lagrange times our data points y sub j. And we sum this 0 to n in the discrete case. So fairly simple. As long as you know the Lagrange form, then you can just plug in your values to that and then calculate the sum. And it's just a discrete sum, so you'll probably just have like a second order polynomial, and you just add them up, and that's how you get your coefficients. And this method is definitely better than the monomial basis, but we're now going to go to another method that is slightly better than Lagrange and monomial. So the next method, and probably it can be the most like tedious, I guess I would say, even though it's fairly simple, is Newton polynomials. So this is an even more stable approach than the monomial basis, as I mentioned in a Lagrange interpolation. And we want to use something that's called a Newton polynomial. And I mentioned that we can't express these polynomials as a linear system, but I don't do it in this case because the linear system is not as easily defined as like the van der Rohe matrix. There's a lot of zero terms, and I think it's just better to use what I'll be calling divided differences, or not I'll be calling, that's just what they are. They're called divided differences. So here I've listed the general form of the Newton polynomial, so the nth case, and hopefully you'll be able to recognize the pattern. So we start at a naught, just like our general form of the polynomial. Okay, that's fine. Then we go up to a1, and then we are timesing times this term x minus x naught. So now we go to a2, and we include x minus x naught again, but now we include x minus x1, the next term. So if you could see the pattern, if we go up to an, we of course have x minus x naught, x minus x1, and then we do that all the way up to x minus xn. So you can imagine that a3 is x minus x naught, x minus x1, x minus x2. And so this is a Newton polynomial. And I list here what a second order Newton polynomial would look like. So p sub 2 of x, a1 x naught, x minus x naught, x minus x naught, x minus x1. And so we use divided differences because this way of expressing it can get very tedious as far as finding the coefficients go. So we generally denote this as I want to see if I can zoom in. So we generally denote this with a bracket notation. So we define the coefficients a naught as f bracket x naught, which is really just y naught. And then f for our coefficient a1 is f bracket x naught x1. So this looks like an interval, this bracket notation, and that's y1 minus y naught, x1 minus x naught. And so you can see how these terms keep growing. So that's why we use this divided difference notation. And generally we can, if you're like doing this by hand, it's nice to set up tables just to keep track of everything. So this is why I think at least it can be kind of confusing. It's just tedious, but it's not actually difficult. It's just your the actual numbers that you're calculating are really easy, but you might be getting caught up in all the terms. So these are all the basic interpolation methods I wanted to mention. I will mention another one, which is splines. But as I mentioned at the beginning, these are the very basics of interpolation. And so while these techniques are useful in their own right, we now see more and more mathematicians finding better techniques, newer techniques, or at least optimizing these techniques as much as they can. So the next thing I wanted to talk about was splines, and this is a far better method of interpolation than all the other ones we previously discussed. It's a little bit more involved, but as long as you understand what piecewise functions are, or you might hear them as step functions, then it's not too bad. But I guess I'll just get right into what we want to do with splines. So again, we're still trying to interpolate a function. So essentially find an approximation to a function at every point. So we do want our interpolation to cross every data point. That would be ideal. We'd get the smoothest curve. And we want a polynomial because we're doing polynomial interpolation, but we do not want a high degree polynomial, which I'll discuss later. But let me zoom in still. Okay, so we do not want a high degree polynomial. And so I sort of listed down like what we want to do with this. So again, our problems always start the same. We're given a set of points, in this case x and y. Degree of smoothness, we don't really need to worry about this definition. This is more of an analysis definition. But we want our output to be a continuous piecewise polynomial, which in this case we call s of x, s for just spline. So the idea behind this is that the degree of the polynomial is fixed. As we mentioned, we don't want a high degree polynomial, so we're going to put a restriction on it and restrict the degree of the polynomial, but we still want to satisfy our polynomial equal to y sub I, in this case s of x sub I, and that's for all points. What did I say here? Oh yes, so in this section I'm sort of just giving a general overview of how to define splines, but I did mention this because there are things like cubic splines and first degree splines and second degree splines that are on their own, like used specifically for different things, even though they're just types of splines. And so I'd say they warrant their own discussion as far as calculation goes. But again, I'm not trying to show calculation for everything. I'm just trying to give an overview. So let's just start with the definition of what a spline is. So as previously mentioned, we want to limit our polynomial to one variable. In this case, a spline is considered a piecewise polynomial function, which we call capital S. It takes values from an interval a to b and maps them to R. So again, we're just talking about some transformation, a linear transformation from values from a to b to R. So I think you would call this a coordinate function, where you're just mapping real values to real values, because a and b are going to be assumed to be real numbers. So I guess you could say that S is a coordinate function in its purest form. And I wanted to outline just a general proof for this, of how we can actually define this piecewise polynomial. So because we want S to be defined as a piecewise function, let's let the interval a to b be covered by what we're going to call k ordered disjoint subintervals, which is sort of an ugly way of just saying subintervals. We don't need this disjoint or ordered. So we want the interval ti plus 1, so our first instance and our second instance, for the values I of 0 up to k minus 1. And then here I'm just using union notation because I specifically mentioned that they're disjoint. I wanted to use this fact of the union, which you probably see in probability with disjoint events, but all it means is that we're summing, essentially. You can think of this as the sum, or capital sigma, but it's more of like logical reasoning. So all these intervals, we want a closed interval on both ends, but in between those closed ends, we need values that are in that interval. So they're not entirely on a closed interval. And so we'll see that for the interval a to b, we want a closed interval, but as we're unioning up and up and up, all these other endpoints are open intervals until we get to t sub k, which then we're closed again. So that is to say that the coefficients a, I'm still trying to keep the coefficients defined as a, is just defined as t naught up to tk, and we sort of satisfy this inequality where the one before is always less than the current, which is fine. And we can also say that's equal to b. There is such thing as what we call the A and B vector, but I'm not going to talk about that here. So that is to say that on each k subinterval of the interval a to b, we want to now define some polynomial p sub I, and this will be our piecewise polynomial. So p naught is an element of the interval t naught to t1. P1 is an element of the interval t1 to t2, and that goes on and on and on for the k minus 1 case, which would be part of, well, you guessed it, the interval t of k minus 1 up to t sub k, as we showed up here. So this right here is our piecewise polynomial. I know this is probably not the definition of a piecewise function that most people are used to seeing, usually where you have that big brace on the side and then the values all stacked on top of each other. But if you've seen a step function, this is exactly what that is. Just a piecewise polynomial is a very specific type of piecewise function. It's a polynomial, which we've showed how we get here. So this is what we want for our splines. And so I will mention that there are these things called cubic splines, which involves more than this. We need to show things like the second derivative and the first derivative, and we want to show continuity at certain points on the interval, but that's not what I'm trying to worry about here. I was just trying to give an overview of what a spline is. But once we have our piecewise polynomials, we can then actually construct our interpolation. So, oh yes, I wanted to note that the points t sub I are what we generally refer to as knots. So these are the points that, if I'm thinking of it right, are connected at the x-axis on the graph, would be called knots, or t sub I in this case. So with that, I'll end this discussion on splines, I guess, with the following graphic, which shows a smooth function being interpolated by splines. And so we can see these are different piecewise polynomials. You can see they're not entirely continuous. We have breaks here. These are the knots. And that's really the whole idea behind splines. This is probably how you generally imagine computer graphics, I would guess, is sort of this idea of when you zoom in, you can see the rough edges. And that's what splines are really. It's just taking straight lines and fitting them around a curve over and over and over and over. That way, at a certain point, they look like the curve itself, but they're never exactly the curve. And this, of course, leads into the idea of things like integral approximations, which I won't talk about in this video. It's just the general idea, I think, of approximating in numerical analysis. Just taking things like rectangles or straight lines and then adding them over and over and over until you get something that looks like the function itself. So with that, I've talked about interpolation and I think all the methods I wanted to talk about. So now I wanted to get on to Runge's phenomenon, which is a very cool issue that we see in numerical analysis. Oh, okay, I fucked myself. So, in general, Runge's phenomenon describes a problem of what we call oscillation at the edges or endpoints of an interval that occurs when using polynomial interpolation with polynomials of high degree over a set of equispace interpolation points. So again, a lot of words, but really just means that as we interpolate a function, if we're using equispace points, which means we know the distance between each point, or we're just choosing a set of points specifically, at the endpoints of our interval, so say -1 to 1, at -1 and 1, there will be oscillations. In other words, the interpolating polynomial won't even remotely match the function that we're interpolating. So, okay. In numerical analysis, we're always concerned with accuracy. That's the whole point of it, is trying to find the best approximations possible for the discrete cases, because computers can't just do calculus. So you have to just use a lot of linear algebra and basic math to get it to do calculus, which is just all approximations. You can't just get a computer to perfectly solve an integral as you would on paper, you need to use approximation rules. And so when we're implementing this, we have to worry about the actual issue of like numbers on the computer. So we have to think about things like 64-bit systems or 32-bit systems and like catastrophic cancellation and floating point. And so the last thing we want is to approximate something and have it be completely inaccurate or just return all zeros because the numbers were too tiny. So you get catastrophic cancellation. So generally we want to take as many samples as possible, which gives us the best approximations. And so you would think that for interpolation, we'd want to do the same thing. Like if we have a perfectly smooth curve and we're trying to use splines or something to interpolate it, then we'll get as many splines as possible so that it looks more and more like the curve. We don't want it to look jaggedy around the edges. We want it to just look like the curve itself. But as it turns out with interpolation, there's this very specific thing called Runge's phenomenon where as we try to get more and more accurate, or I said that in quotes, but that's not really what it is. I just thought that was a good way to describe it. As we try to use more and more data points, our interpolation essentially just turns awful. So this is like an odd consequence that I thought was important to mention, and you'll probably learn about in any numerical analysis class when talking about interpolation, because it's a very famous result, and it's how we have to think about interpolation. We have to think about it differently than some other analysis techniques because of this phenomenon. So to understand this, I first wanted to mention some error theorems that are important to actually mathematically describe how Runge's phenomenon happens. So the first one is what I just called interpolation error 1. And so if our interpolating polynomial p sub n of x is the at most n degree polynomial that interpolates f of x at n plus 1 distinct points, and if f to the power of n plus 1 is continuous, and in this case this notation is the derivative, so this is the n plus 1 derivative. So if that's continuous, then we can say that the error, which I've denoted as e of x, is equal to our original function, f of x, minus our interpolating polynomial, p sub n of x. And this is generally how we define error. I think this is absolute error or relative error. I forget. I get the two confused. But generally, if you want to just show error, you can just look at the difference between your approximation and then the actual value. And so in this case, our actual value is our actual function, and then our estimation is our interpolating polynomial p sub n. But we better define this using Taylor's remainder theorem, which I mentioned off to this side, but we define it as 1 over n plus 1 factorial times our n plus 1 derivative of the function evaluated at c, and then we take the sum of the products of x minus x sub I. And that is because of something called the Lagrange remainder, which Taylor uses for his remainder theorem. And I mentioned this not because you need it necessarily for this, but it is how we derive this equation. We use this as a intermediary step or a lemma, whatever you will. So this is the basis behind it. And this is how we define this remainder function. It's the n plus 1 derivative of some term, what is this? Chi, I think this is, over n plus 1 factorial, then x minus a to the n plus 1th power. So that's our first interpolation error theorem, which just defines general error. Okay, so good. Now we understand how error works in a general sense. So now we want to mention something called the bounding lemma. So if we suppose that x sub I are equispaced in the interval a to b for I in the set 0 to n, then we say that the sum of the products, pi, of the absolute value of x minus x sub I should always be less than or equal to h to the n plus 1 over 4 times n factorial. And this is not an n plus 1 derivative term anymore. This is our step. So you've probably seen h defined as like b minus a over n. Like I think it's the mean or the median, but that's what that is in this case. And then finally, we have the second interpolation error theorem. So if we let the absolute value of the n plus 1 derivative at x be less than or equal to some number capital M, then we say that the equispace interpolation error has the bounds of that absolute value of our error, so f of x minus p sub n of x, less than or equal to m h to the n plus 1 over 4 times n plus 1. And again, I'm not going to derive this, but it is just a theorem that we can understand. But really, I would say the only thing you need to focus on is how we understand error in general with this first theorem. So knowing this, Runge's phenomenon is the consequence of two properties of this problem. First, the magnitude of the nth order derivatives of this particular function grows quickly when n increases. Second, the equidistance between points leads to a Lebesgue constant that increases quickly when n increases. I included this just to be specific, but Lebesgue or Lebesgue, this is, I think it's from like measure theory or analysis. I don't even know it, so you don't need to understand it. Just think of it as any constant. So don't get tricked up on the terminology. We see this phenomenon graphically below because both properties combine to increase the magnitude of the oscillations, which we'll see at the endpoints. So Runge's function is specifically what we're looking at, and this is the function that is used to define Runge's phenomenon. And it's a pretty simple function. It's just 1 over 1 plus 25 x to the second power. And so that's what I have on the right here graphed. So the resulting interpolation is then seen as the following. And so this is Runge's phenomenon. So after all the math, this is really what we get at the visual level. So here's our interval, -1 to 1. So we see that at the endpoints, -1 and 1, our interpolation is very bad. So the red is Runge's function, 1 over 1 plus 25 x to the second. And then this blue is a high order interpolation, and this green is an even higher order interpolation. And so we see that, yes, as we increase our order, our interpolation does get more accurate here. We see the blue it covers a little bit of it, but not much, but then it gets tighter and tighter as we go up in higher order terms. So our approximation is better here, but then we see that at the endpoints, we get a horrible oscillation. Our error gets worse and worse between our original function and our interpolating polynomial. And at cases like n equals 30, like extreme cases, the interpolating polynomial isn't even like recognizable with the function because of the endpoints. It just doesn't read. It looks like a sine wave and then just a straight line. So it gets even worse and worse. And so this is the whole idea behind Runge's phenomenon and interpolating errors in general. It's sort of like the anti-intuitive idea that as you try to get more and more accurate, you actually get a worse and worse interpolating function or polynomial. So that's something we have to deal with, and there are ways to deal with it, which I didn't mention. You could use things like Chebyshev nodes, which are like fixed points, which should help your interpolation, but generally it's something that you just need to keep in mind when interpolating. So you'll often find that your best interpolations are somewhere in the middle between your lowest and most extreme case. And you use this math to determine what's the best. You want to minimize the error, which would involve some more calculus. But I wanted to treat this sort of as just an overview of interpolation and Runge's phenomenon. I didn't want to actually go into any problem solving. I guess if maybe in the future I'll show a video of like me implementing like MATLAB code for an interpolating polynomial, but I'm not sure yet. But I thought it'd be fun just sort of to like make it, and I really like the subject at least, so I wanted to make something for me to keep in the future. But if it helped anybody, then that's always cool. So yeah.